So this video is the first video of chapter 6. You can see the topics here: bonding, types of bonds, naming covalent compounds, and Lewis structures. So in the first part of the chapter, we'll talk about the difference between the two types of bonds, ionic and covalent, and then more specifically nonpolar and polar covalent bonds. And then we'll focus more on covalent compounds after that. Next chapter, we'll dive into ionic compounds. So let's get started here. So the first type of bond we'll talk about is an ionic bond. Now, ionic bonds have crystal structures, so that's why the word crystal is there. Now, it is a chemical bond resulting from the electrostatic attraction between positive and negative ions. So what happens is you have a bunch of positive and negative ions in the crystal, and when they pack together, they are attracted to each other, and that attraction is what holds them together. So this type of bond forms when atoms gain or lose electrons. And what always happens is one type of atom will lose their electrons and one type of atom will gain electrons. And that's what results in some of them being positive, some of them being negative. Now, typically the atoms that lose electrons are the metals, and the atoms that gain electrons are nonmetals. But if I say ionic bond, first thing you should be thinking is electrons are being transferred. So electrons transferred, ionic bond, those two phrases should, or two things should go hand in hand in your mind. Ionic bond, electrons are transferred. So Mr. Crone has a good analogy on how this works. If you have the bully on the playground, if you got a much stronger kid, they will steal the toys away from weaker kids. It's the same is true with atoms. The bullies, there's some atoms that are bigger bullies on the periodic table, and they like to steal the electrons away from the weaker elements on the periodic table. And that word, the atoms that are bullies, we say that they're very electronegative. So that's why the word electronegativity is there. We'll talk about that soon. So one atom will take the electron away from another because one is stronger and it is kind of a bully like that. Now typically, like I said, it's a metal and a nonmetal. The metal is usually what loses electrons, the nonmetal is what gains electrons. Or it occurs between a metal and a polyatomic ion, which the word polyatomic ion is new to you. We will cover that later as well. So ionic bonds, like I said, you get the opposite charges. They will pack together to maximize the attractive forces, and so their crystal structure is arranged in a way so that the positives and negatives are as close together, and the positives, and then the negatives and negatives are as far away apart. So opposite charges are closer, negative or similar charges are far apart. Now, individually, the force between the atoms is weak. That's holding them together. The ionic compounds get their strength in numbers because when they pack in crystals, there's so many of them, a lot of little weak forces adds up to a very strong crystal. So an example is NaCl. The forces holding the NAs and the Cls together is very weak, but because there's lots of little attractive forces, the crystal structures for sodium chloride are very strong. It's hard to break those crystals up. So you can see here, they pack in a way that the positive charge is surrounded by negatives and they're attracted to it. And notice that the positive are as far apart as they can be. So you got the positive is surrounded by the negatives here, and then the positives are a lot further away. So that's how it maximizes the attractive forces. So what you need to know is there's no individual bonds between the atoms. So there's no individual bond linking these two atoms together. It's just kind of a net attractive force that holds them together as they're packed in there. And this force we call the lattice energy. It's the energy holding the ions in place. That's called the lattice energy. Or another way to think about it is that's how much energy it takes to break the crystal apart. In this slide, I give you some examples of different ways that ionic compounds can pack together. So the crystal structures are the packing arrangement. On the left, you'll see calcium and fluorine, or calcium fluoride, and on the right, you'll see magnesium oxide. Now, the way in which they pack is determined by the charges, the relative charge of each atom, and the relative size of each atom. So depending on if there's two similarly sized or one big, one small, you'll get different packing arrangements. We don't get into the details of how they packed, but there's a whole section of chemistry that talks about the different packing structures that atoms can make. But you can see here in the 3D structure that you got your positively or negative ion. In this case, would be the positive ion is packed around with the negative oxygen atoms. Okay, so electronegativity is going to be the next thing that we cover in this class, or in this video. Now, electronegativity is the measure of the ability of an atom to attract an electron in a chemical bond. It's basically how bad does an element want electrons. So when it forms a bond, some elements are better at pulling in electrons and some aren't as good at it. This is a measure of how good each atom is. There's a whole scale on it that we'll get to. It's on your yellow sheet that we're going to be pulling out here shortly. So it's how bad the atom wants the electron. It's the bully scale. Remember we talked about the bully pulling the electrons from the weaker atoms? We were referring to electronegativity there. It's kind of like the bully scale. Now there is a trend to this as well. It increases up and to the right. This includes the entire periodic table except the noble gases. The noble gases don't count in this trend. They don't want electrons, so they have zero electronegativity. The rest of them, though, they have a varying level of need for electrons. Fluorine is the most electronegative atom. So if you go up and to the right, so if we go to the right and we go up, you see fluorine is the most electronegative. That would leave francium as the least electronegative. So that's how you tell that. Now, why the trend? As you move down a group, the electron feels less attraction. Do you remember that as you go down a group, so as you go down a group, the elements get more layers? So as you go down, they get more layers. So if this was lithium, sodium, and potassium, potassium is going to have an easier time letting go of an electron. It's harder for potassium to keep its electrons. It's because it's bigger. The electrons that it's losing or trying to gain are much further away from the nucleus, so it has a lower electronegativity. It's less good at pulling in electrons, so it's lower electronegativity. Now as you move to the right, so as we go to the right, they get closer to having an octet. So you've got one valence electron, 2, 3, 4, 5, 6, 7, 8. Remember, the noble gases already have 8. They're happy. As we get closer, though, 3, 4, 5, 6, 7, they get more desperate. It's easier to pull in one electron versus 2. So it's very similar to the reasons of the reactivity trend of the nonmetals, if you want to go back and look in more detail at that trend. Now, a covalent bond is the other type of bond other than ionic. So in an ionic bond, the electrons are transferred. They get stolen. So covalent bond is the opposite. They decide to share. So it's all about sharing in this case. So covalent's all about sharing. So this is like juniors and seniors on the playground. You guys have figured out how to share your toys at this point, hopefully. So an example here, we've got a hydrogen molecule. You can see that each one has one electron, but when they combine, the electrons spend equal time around each. So each hydrogen is sharing one electron. And so what that means is that when it shares, this bond represents 2 electrons. 2 electrons. I'll put E minus. And so then each hydrogen thinks that it has both electrons. It's happy. That's how that works. So here's some examples of covalent bonds in action. You can see the hydrogens. Each one has 1. they want 2 to be like helium, so now it thinks that it has 2 valence electrons. The chlorine atoms, they share these 2 electrons right here, so I'll let it replay again. After they share those 2 electrons, now each chlorine, if you count, it thinks that it has 8. It's happy. It thinks that it's like argon. And then if you go down here, here's another example. We've got carbon. It has 1, 2, 3, 4. It shares 1 electron, each with 4 different hydrogen atoms. So now if you count, it thinks it has 8. So there you go, 8. It's got 8. Same thing, water. That's how a covalent bond works. Now, one thing about covalent bonds is there is an individual link linking these 2 atoms together. There is an individual bond holding them together. It's a shared pair that links them together. So if you remember ionic compounds, there's no individual bond. They're just naturally attracted to each other, but there's nothing like a pair of electrons actually holding them together. But in a covalent bond, there is. You'll have individual bonds holding the atoms together. So that is where we will end this video, and then we'll talk more about the difference between ionic and covalent, why one happens sometimes and why the other type of bond happens another time in the next video. So for now, just know ionic compounds transfer electrons, covalent shares electrons, and electronegativity is a measure of how badly the electrons want, how badly the elements want electrons when they form a chemical bond. And that is where we'll end here.